Hi, everyone. So this is our last talk of the spring session. So again, this talk series are given by the awardees of NCU-Delta Young Astronomer Lectureship, which was founded by the National Central University and Delta Electronics Foundation to recognize young scholars who have made outstanding contributions in this field. So each year, the new awardee will be invited to Taiwan to give talks and interact with us. So the original plan was to invite all of the previous awardees to come back to Taiwan, but unfortunately, we have to make this event online due to the pandemic. So our speaker today is Professor Shen Yue from UIUC. So Professor Shen received this award in 2018. I think he's a world expert in quasars and supermassive black holes. And I believe he works on a lot of topics and a lot of things related to these fascinating objects, such as their physics, how they evolve with time, and how they interact with the host galaxies. So it's our great pleasure to have him here. So the title of his talk today is the galactic-scale supermassive black hole pairs at cosmic noon. So just a few announcements here. Please mute yourself during the talk. If you have any questions or comments, please leave them in the chat box. We will come back to those questions later or during the Q&A session. All right, Professor Shen, I'll let you take this away.
Okay, great. Thanks very much, and also thanks for the invitation. It's my pleasure to be here again in this virtual mode to talk about a topic that I have been working on for the past few years. And I choose this topic because, well, first of all, it's interesting, but also, as I was saying earlier, there's a lot of efforts led by students from Taiwan, in particular, Yuqing and Xiangzhi. So they have been playing a major roles in carrying out the observational program and performing data reduction and analysis, and also writing up publications. So the topic is about galactic-scale supermassive black hole pairs. So that's not just one supermassive black hole, but two at cosmic noon, which is around redshift of 1.5 or 2. I'll get to that later. I do want to mention that a Zoom talk is often awkward because I cannot see the questions posted on the chat. So if Yanchen, you see any questions there, feel free to interrupt me and sort of give me some feedback so we can have a more interesting discussion on some of the questions.
Sure.
All right. Yes, thanks. So let me get started. I will just say that first I will give you some basic background of this topic, and then I will dive into some specifics, some details of supermassive black hole pairs and why they are interesting, and what we already know and what's missing in the grand picture. And then I will present some of our own latest work, and I will end with a sort of positive outlook where this is going, and why do I believe that we will have a definitive answer to some of those questions related to this topic in a few years. Okay, so let's get into it. All right, so I'd like to start with some eye candy first. This is a simulation, cosmological hydrodynamic simulation taken from the Elytris project. And the purpose of showing this simulation is to show that we live in a hierarchical universe. So structures build up from bottom to up. The smaller structures form first, and they merge and combine to become larger and larger structures, and throughout the history of the universe. So what's shown here, the end product at a ratio of 0 is a giant elliptical galaxy. So it's a dead and red galaxy. But what we'll see in this animation shows the evolution or the formation history of this giant elliptical from high redshift. So you can see that as time goes on, smaller and smaller galaxies shown on the left there's a starlight, and on the right are the distributions of gas. So the giant elliptical gas at redshift 0 is built up by the mergers of many smaller galaxies. Most of them are spiral galaxies in early times. And as you can see that when two or multiple spiral galaxies emerge, then they undergo not only morphological changes, but also the merger is triggering violent star formation to form new stars. And the individual stars formed earlier will eventually become the ingredients of the final giant elliptical galaxy. So the details of this simulation are not important. And the important message here is that galaxy mergers happen very frequently in the universe, and in particular in the early universe, when the specific merger rate per galaxy is much higher than the merger rate at the local universe. All right, so the other side of my story concerns the supermassive black holes at the center of galaxies. Well, let's be more specific, at the center of a massive galaxy, because we don't really know if small dwarf galaxies also have a supermassive black hole at its center. So for several decades now, astronomers have come to the realization that the existence of supermassive black holes at galactic centers is quite ubiquitous. And this is done through demographic studies of nearby dormant galaxies. And when they look into the central regions of those dormant galaxies, they find dynamical evidence that there must be a very compact and very massive dark object in the center, because the stellar orbits around them tends to be moving very fast. And it's not just that, there is also a remarkable correlation between the mass of these dark objects, which are called supermassive black holes, and the properties of the host galaxies. For example, the gravitational potential of the galaxy, the stellar mass or the stellar velocity dispersion of the bulge of that galaxy. So this is famously known as the correlation between black hole mass and galaxy properties, or one of them is called the M-sigma relation, which is shown here. The y-axis is black hole mass, and the x-axis is the stellar velocity dispersion. So you can see over several orders of magnitude in black hole mass, then there is a correlation. It's kind of strange because the region that can be affected gravitationally by the black hole is tiny. It's only on the order of 10 parsecs compared to the size of the galaxy. So the reason we're seeing a correlation here over many orders of magnitude in mass is telling you something. Perhaps there is a causal link between the growth of the supermassive black hole and the formation of stars in the host galaxy. So if we look at our backyard, then the closest supermassive black hole to us is, of course, the black hole at the center of the Milky Way. And this is actually one of the supermassive black holes for which we can precisely measure its mass. It's about 4 million times the mass of the Sun. And this is made possible by monitoring the orbits of individual stars around the center of the Milky Way. If you have enough spatial resolution with AO imaging, you can actually see through the dust and the heavy extinction in the optical towards the galactic center, and see the orbits of individual stars over years around a central dark object marked by this star here. And based on the orbits of these stars and applying some Newtonian dynamics with some GR correction, we can measure the mass of that central dark object here, and to be roughly 4 million solar masses. Okay, so but until at this point, the first two images here is telling you that, well, there are supermassive black holes at the center of galaxies. But those are based on dynamical evidence that the motions of stars or gas are surrounding that central object are so fast, so it has to be a very massive black hole there. But seeing is believing, so this is why it's important. It's amazing to see the first direct image of a supermassive black hole in the nearby giant elliptical galaxy M87 about a few years ago. I believe it's in 2019 when the Event Horizon Telescope project released their first direct image or first portrait of a supermassive black hole in M87. And what is seen here is an incredibly small region, compact region in the center of that M87 galaxy. And you can see that there is a bright ring surrounding a kind of central shadow area. And that black spot in the middle is called the black hole shadow. And that's the shadow cast by the black hole onto the surrounding accretion flow. So the black hole at M87 is not entirely dormant. It is accreting very tenuous gas onto it. And this tenuous accretion flow is producing that glow you see in this orange bright color. And by measuring the size of that ring, it's called the photon ring, you can infer the mass of that black hole, the event horizon as well. And it agrees with the measurement of the black hole mass measured from the stellar kinematics, okay? So the size of the photon ring in this M87 black hole is about the size of the solar system. And that gives you a rough estimate of the mass of about several billion times the mass of the sun. So it's a gigantic black hole in the heart of M87. So what about the Milky Way center black hole? So just a few days ago, the Event Horizon Telescope, I'm sure that you guys have heard of the news. It made such a blast across internet. So this is the first portrait of the Milky Way center supermassive black hole, this 4 million solar mass black hole. So you can see that you can still see that the central black hole shadow surrounded by this photon ring. The geometry looks a little bit different, and the locations of those bright spots also kind of differ from what we see in the M87 black hole image. But the incredible thing about this is that this Milky Way center black hole has a mass that is 3 orders of magnitude smaller than the black hole in M87. So now we actually have 2 portraits for 2 very different black holes in size, but they are both supermassive black holes. So the bottom line is massive black holes are ubiquitous at the center of massive galaxies. So here are our facts. Galaxies merge frequently in the universe, and we also expect supermassive black holes are common at the center of individual galaxies. If you combine those 2 facts, then there is an almost inevitable consequence that the formation of pairs of supermassive black holes is nearly inevitable.